This is the third in a series of videos in which I'm investigating noise on the Altair 8800 computer, and specifically trying to find ways to deal with that noise and make the machine more reliable without changing the design or adding lots more bits and pieces to it. So far in the previous videos I've had a brief look at the issues caused by the physical layout of the machine, and I will be looking at that in far more detail in the upcoming videos. But in this video I wanted to take a look at the way in which different types of ICs that are often found in the Altairs can cause problems. And by different types I mean the various different families of TTL chips that are often found lurking in the Altair. So what I've got here is a couple of breadboards. The top breadboard has 6 ICs, all of which came out of the Altair that I showed in the previous videos. The bottom breadboard is just a simple 74 LS04, and the way this is arranged is I have the top 6 chips all receiving a common square wave signal from a signal generator, so they should all be switching at the same rate and at the same time. The outputs of those 4 devices, they're all 7404s, and the output of the gate that I'm looking at is connected through a resistor to an LED, and the resistor value is chosen such that we're effectively loading it up to about 5 fan-out gate arrangements. So effectively they think they're driving 5 inputs of other gates. They're then fed to the inputs of a 74 LS04, and each of those is feeding one of the red LEDs. They're in the same order, so this output is feeding the 7404 gate that's driving this LED, this one to this one, etc. So they're all in the same order. And what I want to show here is very briefly the issues caused when different families of TTL chips are mixed within the same machine. Now sometimes mixing different families can be a very good thing if you have a specific need to do it, but 99% of the time it's a very bad thing. And that's what I want to show in this video, is that what I've been investigating so far and what I've been trying to eliminate are problems caused simply by inappropriate mismatching of different IC family types. Just as a very brief check, I made this chart. Now I would say this is the second time I've recorded this video. The first time I went through the mathematical functions that you can use to determine which particular family type to use, but it was a bit long-winded and a bit boring, so I decided just to do a practical example. It was hopefully far more interesting. But these are the 6 chip types that we're dealing with here that I have on the breadboard, and as I say, these all came from one machine. Now originally, when the Altair was built, almost certainly they were all standard 7.4 devices, and over the years I'm assuming that various devices have been replaced as the originals failed, or for whatever reason, or maybe when the person built it they could only get hold of certain types, or just picked one out of the bin and plugged it in without realizing it wasn't the right type. So what we've got is a standard TTL, and you can see that on this chart the left hand bar is the input voltage range, so anything above the top of this bar is an acceptable range for a high input, and anything below is an acceptable range for the low input. And then the output bar is the expected output driving nominal loads, and the different coloured areas at the ends assume a 100 millivolt degree of uncertainty, which is quite small. Normally it's far greater than that, but I'm trying to keep this as a fairly practical example. So in other words, with a standard TTL device you'll get an input range that's accepted as being greater than 2 volts for high, less than 0.8 volts for low, and the area in the middle is an area that shouldn't really be used, and you should aim to get your signals through these areas as quickly as possible. The right hand bar is the output values. and you can see that for each different type, so the next one's an LS, so 74 LS series, quite similar, but has a slightly higher output voltage in the high mode and a slightly higher output voltage in the low mode. Then we go on to the HC, so these are 74 HCs. These are the ones that most often cause problems when they're mixed and matched with standard 74 LS or the standard 74 series devices. We then have an HCU, which I was quite surprised to finding there. It's the first time I found one of these in something other than specialised equipment. So I put this in here just out of interest, but it's not something you're probably likely to see, but you can see it's got a quite unusual input and output range. We then have HCTs. So the HCs are CMOS devices as opposed to TTL. The HC was designed for low power operation and high voltage operation. The HCT is a very different family, although HC and HCT often are used interchangeably. The HCT is actually meant to be a TTL compatible CMOS device, and you can mostly mix these with 74 LS series. It's not a good idea doing that unless you have a specific need to, but you can in theory do that. And then the last one is a Schmidt trigger version of the 7404, so 74 LS14. Same pin out, same function, but it's got a Schmidt trigger input. So what I've done is, as I say, set all these up on a breadboard so that we can supply them with a common clock signal. They're all in the same power supply, and they're all feeding inputs to standard 74 LS gates, which is kind of what you normally see on the Altairs when you get a mix and match. It's one of these feeding an LS or one of these feeding an HC or something like that, but the point is it's a mixture rather than all being a consistent type. So I'll switch on the power. I've got it currently set to 5 volts, and now I'll turn on the signal generator. You can't see the signal generator, but I've got it set to 3 Hertz, and currently the low value is 0.5 volts and the high value is 4 volts. So you can see that we're getting sort of good operation, getting nice clean signals on the scope. If we look at the edges, you can see we get nice sharp edges, and they're switching in just a few nanoseconds with some bounce. Other than that, they're looking quite reasonable signals. What I'm going to do now is change the setting for the input signal to the various different types. What I'm going to do is set the input to all the chips, in turn to the expected output values of each type of chip, as if though in the first instance a 74 series TTL chip is feeding them, and we'll see what the effects are. So I'll change this now. So I'll set that to 2 volts high. You can see that channel 2 is actually showing the input value, and now I'll go to the low level and I'll change that to the 0.8 volts, and straight away you can see that we have an issue. You can kind of see what's going on here if you look at the input values compared to the output values, and in particular why the HC version is still working. You can see this is the effective threshold for switching. Now there is a lot of ambiguity in this because it does vary slightly from manufacturer to manufacturer and chip type to chip type, and of course depending on the supply voltage and the fan out that's being used, you'll get different results, but effectively what you're going to see is different behavior depending on the exact results. Now one thing that's causing this strange behavior is that the inputs are not isolated, and you have to bear in mind that the inputs to each of these devices has different circuitry, and that will in effect change the voltage levels going to the other devices. So if I was to start unplugging the different device types, you'd find that the behavior of this circuit would completely change, because the input value being fed to the individual devices is going to be different based on the loading that each input is seeing. So I'll reduce the swing back down to 0.7 volts, and you can see straight away that we've recovered some of the units. The 7414 Smith version is now not apparently working. So just to clarify what we have here, we have the standard 04, we have the LS, we have the HCT, we have the HCU, we have the Smith version, and then we have the HC at the end. So what I'll do now is start to raise the input signal. I'm only going up 10 millivolts at a time. So I'm now approaching what should be standard 7.4 LS range. So we can see here is as I'm changing the input signal with the HCT, which is the one that we are currently monitoring, so channel 1 is currently monitoring the HCT device, and the output is either working to full output values. So if we look at the chart, we'll see that the HCT is swinging from 0.1 volts up to about 4.4 volts, something like that, which is the specified value, and that is actually pretty much what we're getting. But as I change the input, at some point it will stop working. You can see there we're kind of on the edge of instability, but it stops working suddenly, and then it comes back when I increase the signal level again. But if I monitor a 7.4 LS chip, so I'll go to the 7.4 LS, it behaves completely differently. If I start to lower the swing, or rather reduce the low level so it starts to come back into its normal range, I'm doing this 10 millivolts at a time, you'll see that it starts to recover bit by bit. So unlike the HCT, which is an all or nothing, it's either working or it's not, then you can see that as we start to go back into the normal mode of operation, then the output value, because this is the output we're looking at, the output value starts to increase incrementally. It doesn't just come back to its full scale behavior, and that's something I think is not necessarily normally understood with these devices, that it's assumed that they're digital, so the output goes high or low, and it doesn't do that. It will give an output that's to a certain degree dependent on the input swing. And the problem there is it means you get all sorts of weird and wonderful behavior depending on the noise in the system, the voltage drop around the system. All sorts of strange behavior can start coming into play because of the way the different devices behave differently in the different conditions. So you'll have an HCT which either works or will completely stop working, or you get 7.4 series that will sort of incrementally start reducing their output up to the point where the devices they're feeding will start to misbehave. And it can be very difficult trying to pin down exactly where the actual problem lies. Many years ago I once spent 2 entire days trying to track down an error on a £100,000 piece of equipment that was giving spikes in the output readings. It was a spectrophotometer, scanning spectrophotometer, and the output readings every now and again would give a huge spike. Now the system used discrete logic for the A to D converter. It's a huge board with probably 150 devices on it, dual slope integrating A to D converter, and the problem turned out to be that somebody just plugged in the wrong chip type, and the output of that device was sometimes failing to properly trigger the input of the follow-on devices, causing the entire board to misbehave for a fraction of a second. And that's the sort of behaviour you can see, in that it just looks like you're getting noise or instability in the system, when in reality it's just simply the devices themselves that are misbehaving rather than the system. So with the Altair it looks like you're getting problems caused by noise, which is what I thought I was looking at when I first got this Altair, until I started going through the board and then finding this mismatch collection of devices. and once I replaced those, then the entire machine started becoming much more stable. Still very noisy, and that's the thing I'll be investigating in future videos, but this is the first thing to do if you suspect you've got noise issues on your Altair, is make sure that you haven't got a weird collection of devices plugged into the cards. And because a lot of the buses are common, a device in a board that seems to be working might be the one that's causing the issues in the other boards that seem to not be working. It can get very confusing, so it's really a case of trying to eliminate the problem by seeing what devices you have and what the signals are doing. Okay, so I've got the input set back to the standard 7.4 specification, and we're monitoring the output of the 7.4 HCT device, but now I've lowered the supply voltage by 50 millivolts. So currently it's sitting a little bit under 5 volts, but only by 50 millivolts. It's still very close, and it's still within specification. What I'm going to do now is increase the low level input signal by 10 millivolts. We're still within specification all round, but you can see that there's random instability occurring on this particular device. And this is what you'll find in these systems. Now, looking at the LEDs, you can't actually see this. It appears to be behaving itself. And this is one of the things that can easily trip you up if you're trying to investigate this sort of thing. What's odd is you can see that the device adjacent to it doesn't like this noise that it's seeing. It's a Smith trigger, so this is quite sensitive to switching, and that it will switch one way, and then it needs obviously the hysteresis to be overcome before it will switch back the other way. So it does tend to smooth out this type of noise, but that can in itself cause problems. But this particular device that we're monitoring appears to be still switching exactly as you'd expect it to. So this blue LED and this red one, even when it's showing instability, it still appears to be switching. And that can be very misleading. You might think it's working fine if you're looking at the signal with a low frequency device like a probe or something like that, a logic probe. But on a scope where you can see the high frequency, you can see that the instability is quite severe. And this is caused by interaction between the various devices. If we took all the other chips out, it would work fine under these conditions, but because the inputs are all essentially different types of circuits, then they do tend to interact, even though we're feeding it with a low impedance signal generator source. The signal between each one can cause a lot of weird behaviour. This gets even worse if you do want to try this experiment. It is quite interesting, and it will get even worse if you start moving the ground lead supply around. And this comes back to the previous video I made on designing the board for the Altair, in that using a ground plane can eliminate a lot of these issues where you get this strange interaction. So quite often it's not just a case of, well, it's better for the power supply if you have a ground plane. A lot of the time this can just be a simple case of preventing odd interaction between various devices. Now, having said all this, by far the best option, unless there's a very specific need to mix devices, is to stick to one type of device, or at the very least stick to the standard 7.4 TTL and 7.4 LS devices. As soon as you start putting in the other types, especially HC should be steered clear of, then you'll get all sorts of problems cropping up that might be hard to track down. HCs do have their specific uses. They have very high performance in some conditions, but you don't need it for something like the Altair. The Schmidt trigger type can have benefits if you're trying to deal with a noisy signal line, but again, bear in mind it has a much narrower window of operation with regard to input voltage levels. The output's identical to the standard LS, but the input can cause problems if you have issues with voltage swing rather than just noise. The HCU, as I was surprised to see that in there, definitely do not use those. The HCT, in theory you can use them, but again I'd advise not to unless you have a very specific need to. But this is an experiment well worth doing if you're encountering noise on the Altair, or what seems to be noise. Just hook a load of different TTL type devices together and you'll see some very strange behaviour as you vary the conditions under which they're operating. Okay, well hopefully you found that of some interest. If you have any questions on this, then please drop a comment, and in the next video in this series I'll be starting to investigate the noise on the actual backplane of the Altair.